DiGirolamo, and this is my response to the Kaggle Hackathon for Google Big Query AI, Building the Future of Data, where we use Google's BigQuery database system to test out some of their generative AI and machine learning tools in the cloud. So I'm going to be focusing on the AI.Forecast in this particular project. We're going to look at the Google BigQuery UI and dashboard, which is where I run all of the project from, and the GitHub repository that has all of the code that was written for this hackathon. The question that I asked in this project was as follows. With public Lightning data from the NOAA that's hosted in the cloud on BigQuery, and very easy to find Zillow housing data, which Zillow also publishes to the public, could I download that Zillow data, upload it into Google BigQuery, and then look at how lightning and extreme weather might affect housing prices? And if so, could we forecast both? And then see what the forecast capabilities of BigQuery would be, and did it change anything? And so I'm going to take you through the queries that I ran and what I learned in this process. So we'll look at the code here in my VS Code window, and then we'll look at the queries here. The first thing you have to do is download the CSV that contains all the Zillow housing data, and I had to extract or parse the dates the way it was set so that I could pivot it and run it properly in the other queries, and I'll get to that in just a moment. But there is a Python script that allows you to take, if you're going to use a different CSV, I did upload it since it's public use, to the repository, so you can use the original one if you want to upload it and try it. But if you use a new one, if the things have changed and it's been a while since I've made this, you can use this Python script to go ahead and extract and create that very first set of SQL. So here we are, and we're going to unpivot the code. Sorry, I have to correct that. So once you have uploaded in the UI that table, you can unpivot it, and it will give you a table, Zillow states unpivoted, which I have right here, and it makes it so that we can run. See how the columns are here? We need to take those out, and now it's going to be a lot easier to query with the rest of this project. So that's just an important start. It should also be noted that there is a README, by the way, that goes along and takes you through the steps of this project. I have a summary from what I learned and a kind of introduction to what it is that I attempted to do here. This is not a scientifically rigorous test, but it was fun to do. So here we have that pivot. Then we're going to join the two. We're going to join the lightning data from the NOAA with the Zillow data, and we're going to use a BigQuery US boundaries to join them via states. That's what we want. We want to know how much lightning and the average home price for each state. And so we can look in here, and we see this one is join lightning prices. It's important to understand an optimization that I threw into this. I used the $300 credit that was linked in the project page for this Kaggle hackathon, and I ran a query on the NOAA lightning data, and it cost almost $40. It was $30-something, and it took a while. So I've used table sample and cut this way down, but really to demonstrate the repository running. So this sample might be very small for any sort of real decisioning and forecasting, but it's just good for example time. Another reason that or another aspect of this project is I only use SQL and I don't use Python. And to my knowledge of the API right now, and this could be something you could add to this project later, but this was a lot faster to know exactly down here at the bottom. Google BigQuery tells you how large the query is going to be. And like I said earlier, if a query could cost $30-something, you really want to know that before you run it. So I used the dashboard and UI in Google Cloud almost exclusively for this project for that reason. Now you could build dashboards and do a lot more, and I understand that, but for at least this primary query, it was important. For the rest of them, because it's so much smaller, it is less important. So, what does it look like correlation-wise with lightning strikes and state prices? So before we jump into AI, is there something of a validity here? And so it's negatively correlated, which means that the more lightning strikes, the lower housing prices. However, it's not always strong, so you can kind of see here that sometimes it might matter more than others depending on the state. So is it a good comparison? It's a fun example, but there would probably be issues saying that there's validity to some states versus others. So I ran a correlation check just to kind of see, was this kind of a good question to ask? Then we're going to need to forecast the prices. So the forecasting value, the code to run the AI forecast, the AI forecast is right here. And we are looking at the average home value, and we've set our confidence level. And so what we can get from this is a AI forecasted value table. Instead of looking at this right away, we're going to also look at how the strikes were done. So we're going to forecast the lightning strikes. So we want to know how many lightning strikes there might be in a state and what the prices are separately. There is a piece of code in here that joins these with the historical data in one big query called historical union right here. However, when I go to the table, I see there's not there's some not a number. There's some weird null things that go on here. So this is a bonus. The table works for some queries, but it does have some odd things, and I just didn't have time to investigate. So it will run and it will work, but for accuracy, I went ahead and I left this in as bonus code. And what we can do is we can actually just manually, since we ran that, by the way, and this might have an issue to do with it, this historical code runs the AI forecast in it, and it joins everything together. It runs both AI. I don't know if that's an issue or not. It does work, but like I said, I had some odd values come through. So I went through and made sure also that we have to cast all of the dates. Okay, we have to cast all of the dates, timestamps as a date within all of that data. That's an important thing to note. Okay, so we go ahead and we manually join them, and we get a new table, which is all of that housing and lightning data combined. And so let's look at the two results queries. So the first result query is the percent change, and we can look at a lowering of housing values for some states and others go up. Okay, we can see that percent change there. And then the forecasted answers. So if we put together our forecasted strikes and our forecasted home values, what do we learn? And for the most part, given the time, what I have found is that it's just consistent with the historical data. where we have the highest amount of strikes in Texas by far and home values in California. So that's similar to historical data. The percent change is an interesting query as well, so I would spend more time with that. And there's some other avenues we could investigate. So this kind of, just to wrap it up, is my project on GitHub. It's Kaggle Google Big Query AI Conf 2025. My name was Ed DiGirolamo, and thank you very much.